Okay, Bismillahirrahmanirrahim. Now we're going to be focusing on so far we've covered till state transition diagrams, and now we're going to be focusing on types of errors and what they mean with respect to the overall working of the program. Okay, so first of all, when an error occurs, there are different ways that an error can be discovered, and there is a number of different reasons that they may occur. For example, it's obvious that the programmer has made some coding mistake, and it's also possible that initially when we were going over the specifications of the document, the specifications were not drawn out correctly. And then this also possible then the software designer who was responsible for creating the design of the algorithm has made some mistake, and that mistake has been carried on towards the implementation phase. And it's also possible that the interface has been designed poorly, because of which the user of the system is giving wrong inputs, resulting in the wrong working of the software. And then ultimately, there's also possible that this hardware that is the software is running on may experience some failure or some fault, because of which there is an error being occurred. Now, these are different possibilities of how an error, why an error may have occurred. Nothing is perfect. Errors occur. So that's why we do testing. But it's important as to how the errors are discovered. It's very important that the error is discovered before it is deployed at the user's end. Because the worst of the ways in which an error it can be discovered is by the user themselves, because that means that the user has was using the program and has been delivered the software after our inspection and our sort of satisfaction, and it has and an error has been left uncovered. And if that happens, it means that it means it's a poor rep. It affects the software developer's reputation. So the worst possible way to discover an error is that if a user discovers it. So it's better that we carry out proper testing on our end to uncover errors, so that the user does not have to do it. Anyway, so let's look at the uh, different types of error. Before that, we need to understand what error, what Dijkstra used to say about your errors, uncovering errors and testing. So basically, he's a very famous Dutch computer scientist. Some say he is the father of computer science. And according to him, he said that program testing can be used to show the presence of bugs, but never show their absence. So in a way, if your testing is uncovering errors and or bugs, by the way, what is a bug? Bug is a logic error, and we'll be looking through logic errors in a bit. But if it's uncovering logic errors, then your test is working. That's the purpose of testing in the first place. And if you see that you're repeatedly testing your code, and it does not result in uncovering of errors, and then there is a possibility that your test is not up to mark. Your testing strategy should be changed, because no one is that perfect. There has to be some errors that you should be uncovering. So an effective testing strategy is necessary, and uncovering errors beforehand on your end, on the software house end, is very important. So testing strategy and test methods have to be carefully sought out, and they have to be integrated throughout your program development life cycle, so that at each stage you progress with without errors. And a very important aspect to note here is that the earlier you are capable of highlighting errors, the easier it is to solve them. So if I have an error in the, say, the requirement specification phase, or the requirement or analysis phase, that's cheap. That's way cheaper compared to having to uncover an error at the maintenance phase, because later mistakes are more expensive to solve, and maybe if I try to correct those mistakes, it may cause other problems. So it's easier to correct errors early on in earlier stages. Now let's talk about the type of error. One of the most obvious types of errors is a syntax error. And in fact, not only is the obvious type of error, it is the easiest one to solve as well. Why is it easier? Well, first of all, what is a syntax error? Syntax error, it means that you have basically made a grammatical error. What type of grammatical error? In simple terms, you can say that the programming language that you are using, you have made some mistake in writing the program code. You have made some mistake in using the rules to write that programming language, because of which your code will not run. Now, why is this syntax error easier to highlight? Well, first of all, when a syntax error occurs in your program will not run at all. It halts right away. So if you're using a compiler, then your code will not run at all, because during the initial pass in which your code is being analyzed, the error will be uncovered and your program will not run. If you're using an interpreter and line by line execution is carried out, your program will halt as soon as it reaches the line with the syntax error. But the thing is, you don't have to worry about whether or not the syntax error is being uncovered, because the language you're using, the integrated development environment you're using, is very good at highlighting syntax errors itself. Not only does it highlight the syntax errors, it points out the exact line where it's occurring, and it also gives possible solutions of what to do to solve this problem. So syntax errors are very easy to solve, and in a sense they just mean that you have violated the rules of the programming language you're using. So for example, in Visual Basic, whenever a syntax error occurs, it gives this blue underlined representation, and as you can see here, it's also giving a suggestion that what should be done to solve this problem. So it's relatively easy to solve. The difficult part is whenever you have to solve either a logic error or a runtime error. Now, what is the difference between logic error and runtime error? Well, in simple terms, logic error causes the program to run. And by the way, logic error is what is known as a bug. And debugging is the process of removing these logic errors. So basically, logic error means that the program is written, it's running, it will run, it will produce a result, but the result that it produces is not as expected. Now, obviously, when we start carrying out testing, we have some expectations from the program. We know that it's going to do certain things. And if it does not do certain things, it does not produce certain results, there's obviously something wrong with the program. So we have to carry out careful testing to uncover any such errors if they exist. But the thing is, for finding logic errors, the language or the IDE that we're using doesn't necessarily help us. We are the better judges of whether or not something is not working as expected. We have a clear vision of what the software is supposed to do. And if it's not performing as according to our expectations, it's considered a logic error. So first thing is to identify whether or not there is a logic error. Then second thing is to trace where the logic error is occurring. So this is a relatively difficult task because we are responsible for carrying out ourselves, and our IDE that we're using, integrated development environment, has little to do here. It doesn't help us that much. It provides us some tools. We have debugging tools and debug windows. We can use breakpoints and stepping to step through line by line execution to try to find out where that error might be occurring. But overall, we are responsible for highlighting the errors ourselves. Secondly, there's another type of error which is known as a runtime error. Now, runtime error, first difference I need to make clear is syntax error. If a syntax error occurs, the code does not run, it stops, right? If it's compiled language, will not run at all. If it's interpreted language, it will halt as soon as it reaches the line that has the syntax error in it. On the other hand, logic error causes the program to run completely and it produces a result, but the result is not as expected. In runtime error, the code that we're running, the program that we're running crashes. Now, what do you mean by crash? Crash means it stops unexpectedly while executing. So when a runtime error occurs, it means that it was provided with such an input that is not capable of solving, it's not capable of processing, because of which the code crashes. Now let's just say, for example, we have created a calculator, and the calculator requires that we enter the first number and the second number and the desired operation that we want to perform. Let's just say I entered the first number a, second number 0, and since I'm giving inputs, it is safe to say that the program is running. So that I gave in the first number, the second number, and the first number was say 5, the second number was 0, and the code is written in this in such a way that the operation that I enter, whatever operation I enter, is supposed to be carried out first number operation, second number. So if I say, for example, add choose addition as my operation, so it will be first number addition, second number, and the result is produced. Say the code was written this way. I provide the first number is 5, second number is 0, and the operation I choose is division. So that means is that I'm doing 5 divide by 0. Now, as we know that 0 is not mathematically possible to divide. You cannot divide any number by 0. Because of which, when I do this and my code was running, my program was running, only that's why I was giving it inputs. Now, because of this, giving a 0 as the divisor of the, or the 0 as the second number, and division as the desired operation, it will cause my code to crash, because division by 0 is not possible. Now, this is an example of where a code, this is a runtime error. The code is running. There's no syntax error. If it was syntax error, the code will not run, but it's running. But it was given such an input because of which the code suddenly crashes, or it comes to an unexpected halt. It's also another example could be that, for example, we're performing bubble sort, and we, in our loop in which we're comparing elements, we access an index position that does not exist in my array. This will cause my code to halt, because it will access an index position which does not exist in my array. And that's one example. Similarly, if we're doing text file accessing, and we're accessing a text file that doesn't exist, we accidentally write the wrong text file name, and these are all types of runtime errors that will cause my code to crash. Okay, now both of these types of errors, either runtime or logic errors, can be carried out by careful testing. The danger of such errors is that they may show up only under certain circumstances. If a program crashes every time it is executed, it is obvious there is an error. But the if program is used frequently and appears to work until a certain set of data causes malfunction, then that is much more difficult to discover without perhaps serious consequences. Well, very interesting. If, say, for example, a condition occurs only until very, distinct situation, very distinct logics, that means that such type of problems are kept usually ignored while they're being tested in my at the software house. And so they're so rare, those situations are so rare, those conditions are so rare, that they are often overlooked while testing. And if that situation occurs on the user side, then that error may cause, serious consequences. Okay, now let's look at some testing methods. With one interesting testing method is known as stub testing. Now let's just say that I I have many subroutines in my main program, and then there's a main program that is calling all these subroutines. And I just want to make sure that if my main program is working properly and it is calling the subroutines properly, and the subroutines, the code in the subroutine has not yet been written. If that comes later, but I just want to initially check if my main program or the calling program is working properly or not. To make sure the calling program is working properly, and without having to have written the stubs without having written the subroutines, I can use a technique known as stub testing. Now, basically, as you can see here in this Visual Basic syntax, you can see that I have different modules. For example, enter new student, amend details, print list, and search by name. And this is my main program that is calling all of these subroutines. So essentially, my focus here is to make sure whether or not my main program is calling these subroutines properly, as properly. By properly, I mean that when a certain condition is met, a certain subroutine has to be called. Is that subroutine being called properly or not? So just to make sure that is happening, we can write stubs. Now, what a stub is, that basically this subroutine, it's meant to do something else, but we're not sure about this. We were just getting, we want to make sure that the main program works properly, and we want to write these subroutine details later on. But right now we just want to see if the main program is working properly. To make sure that is working properly, we can implement some stubs. Now, what a stub is, that the subroutine is written, and the subroutine simply has one instruction written in it, and that instruction is giving just an output representing that this subroutine has been called. Now, of course, enter new student has other things to do. There are other instructions to be written here as well. The main purpose of enter new student is not just to print this line. It has other things to do as well. But right now, just to make sure that enter new student is working, I just simply write this prompt. So what happens is that when this main program calls enter new student, I will know this. I will know if it is properly calling it or not if this prompt is being printed on the screen. So I can just simply tell by calling these stubs if they are being called properly or not by their relevant prompts being printed on the screen. They are supposed to do something else, but that comes later. Right now, I can just make sure if my main program is working properly by simply writing these prompts in these stubs, in these subroutines. And each time a particular subroutine is called, I will know by their relevant prompts being printed on the screen. So that will give me a good idea if whether or not my main program, which is meant to be calling these subroutines, is working properly or not. Then we have another technique known as black box testing. Now, black box testing means that there's two methods, by the way. This is black box testing and white box testing. But when we talk about black box testing, we have to think of the code as a black box. And what that means is that my tester does not have access to the source code. They just have access to the working program, possibly just the exe version of the program, and all they can do is basically carry out execute the program, give it various test values, and see is it working properly against those test values. Obviously, each test value of the person testing the code has to have a fair idea of what the program has to do against each value. So only then he or she is capable of judging whether the program is working as expected based on that input value. Okay, but the thing is, the tester does not have access to the source code. So that means the coder themselves are not going to be performing the black box testing. This black box testing has to be carried out by someone other than the coding parties. They are not accessing the source code. In fact, they may not even have the technical skills to access the source code. What all they can do is simply give the inputs to the software and judge whether it's working properly or not based on the outputs generated. Okay, now for black box testing to be successful, the a carefully planned test data has to be carried out. This test data should be, covering all aspects of the working of the software. So if your test data should highlight whether or not your software is working properly under normal conditions, whether or not it's working properly under extreme conditions, and most importantly, whether or not it is uh, generating as expected, generating expected errors under erroneous or abnormal values. So based on these expectations, our test data also has to be of this type. So when we give our software the test data for black box testing, we have to categorize the test data in three categories. Our normal values, in which the software has to be performing normally, extreme values, in which it works, but if there are certain precautions to take in extreme values, those extreme values has to be, in extreme outputs have to be presented. And finally, erroneous or problematic errors, inputs that cause errors. And we have to see if whether or not those inputs are actually causing errors. If they're not causing errors on the wrong inputs, obviously there's something wrong. So test data we'll be looking in a bit. Okay, so this is black box testing. The coder has no, as a, the tester has no access to the source code. They will simply provide the working software with different types of test data, normal, extreme, and abnormal values, and see based on those values, is the software working as expected. And they're not, and simply the whole program is simply a black box to them. They have no details of what's happening inside. On the other hand, if we are carrying out white box testing, that means the tester has access to the code, and they are simply working through each part of the program code to try to highlight any possible errors. So let's just say, let's look at an example here in which we're carrying out white box testing. The program here, it says that I am inputting three numbers, number one, number two, number three. So if number one is greater than number two, then I have another possibility that number one is bigger. And if number one is even greater than number three, then number one is the greatest. Okay. Else number three is bigger. So if number one is greater than number two and number one is greater than number three, then number one is the biggest. Otherwise, you can say that number three is the biggest. So that's one possibility. Else, if number two is greater than number three, then output number two is biggest, else output number three is the biggest. So these are the possible, this is my source code. Based on this, I have four possible, outcomes, the four test values that I could use. So I can, for this program to work, I can work out four different possibilities. The first possibility is keeping in mind that the first numbers will be the largest. The second possibility is that the first number is larger than the second number and the third number is the largest. And the fourth possibility is the second number is the largest, and sorry, third possibility is the second number is largest. And the fourth possibility is the second number is larger than the first number and the third number is larger. So these are the four different possible test data that can be used to work out all of the paths in this program code over here. So obviously these test data were formulated based on this source code, and this is the essence of white box testing, that I have access to the source code and I want to, if I want to see if all possible alternate paths are being executed properly, and these test values will help me reach all of the alternate paths here. So let's just say here, I first test data in which the first number is largest. As you can see here in the test data one, my first number 15 is the largest. So in my first, and then we have number two is 12 and number three is 8. So in the first test data in which the first number is largest, my first condition says, is number one greater than number two? True. Is number one greater than number three? True. In that case, this path executes, that 15 is output as the largest. So this path is working as expected. Okay, that's clear. That's fine. Now I want to see if this path works properly. For this, I will use this test data. Now this is my second possibility, that first number is larger than the second number and third is largest. So in this case, you can see the first number is 12, second number is 8, but the third is the largest value. Now let's just see if this path is being reached as expected. Is number one greater than number two? True. Is number one greater than number three? False, as expected. And do I reach here? Yes, I do. I will reach the else state in which number three is output as the largest. Yes, number three is output as the largest. Okay, so this is working properly. Now let's just see if this is working properly. For this, I will use this test data. What does this mean? The third possibility of the third test of data should mean the second number is largest. So is second number largest in this set of data? Yes, it is. So I ask this condition first. Is number one greater than number two? Is number one greater than number two? False. This condition will not run, this will not run, this will not run, but this condition will run. Is number two greater than number three? True. Output number two is the largest number over here. So okay, it's working as expected. Now we've got the fourth set here in which the second number is larger than the first number, second number is larger than the first number, and the third number is the largest. So as expected, that's also fine. So in this case, I will do this. If this condition runs, if number two is greater than number three, number two is greater than number three, false as expected, then I will come here in the else state in which I'm outputting number three as the largest. So as you can see here, using very carefully laid out test data, I am thereby executing all of the alternate paths. And to carry out execution of all possible paths, we needed fourth possible test sets of data that highlight all possible paths. Now, of course, this sets of data is relevant to this problem alone. Now, for other problems, you will have to work on with other sets of data. But again, this is the essence of white box testing, that I will not be able to decide what test data to use if I don't have access to the source code. So that's why white box testing requires the tester to have access to the source code, and based on their understanding the source code and all possible alternate paths, the tester will choose these different types of test data to try to reach all possible alternate paths. By doing so, if there is some error in any of these in the logic, if there's some hidden logic error in the code somewhere, accessing all alternate paths will somehow highlight that error.